Okay, welcome everybody for our Crash ROMER talk on Tuesday. Today, some of you already know I made a lot of talks and presentations about magnetics and magnetic robots, and there are most of the time quite magical things. And today we have Hamdi Uçar, Mr. Uçar with us. He is working on these magnetic systems, and actually will present us one of the most magical looking examples of magnetic systems. You will see Mr. Uçar is born in Istanbul in 56 and graduated from Istanbul Technical University in 80. And since then he's working as electrical engineering in the industry. And as I understand, in late years he got interested in the magnetism and magnetic actuation systems and physics of that, and actually write a really nice paper on a new way of actuating magnetic systems. And he will present us his experience on that. I mean, for many of us, writing a paper is about having a master degree or PhD degree, but I think for Mr. Uçar it's mostly about now with passion and excitement about sharing his information and knowledge, and I hope he will share with us today as well.
Thank you.
So stage is yours, you can.
Okay. So first, this is I call it magnetic bound state. That is a body, a free body, can be held in space through magnetic interaction, force field. As you know, it is not possible to make such a thing due Earnshaw laws. Is forbid, but it's Earnshaw law about static interaction and dynamic interaction. Everything is possible. So this is also a dynamic interaction, and in dynamic interaction, little detail, the inertia of the body enter the dynamics, the equations. So actually, when moment of inertia and force field can be together, it is possible to make some equilibrium, find equilibrium. Most common things is orbital motion. Only there is no also stable possibility with only gravitational field to hold two astronomical bodies, but with rotations it is possible. The inertia of the body solve the things. Right now, okay. So this magnetic, I'm calling magnetic bound state. Actually, it's a term of quantum physics, because in classical physics, before this, there is no it is not possible to make magnetic bound state. Even orbital motion is not possible, because with orbital motion, there is a requirement that force field the variation with distance should be less or equal to power of 3. More than power of 3, it is not possible. Gravitational fields, electrical fields are square power of distance, inverse square. But in magnetics, magnetic interaction always come with dipoles, and when dipoles comes, the power become inverse fourth power because of dipole. Because these things already magnetic. They are previous research, but even Newton and later scientists work, and they found that it is not possible to make any. But even orbital motion is not possible. But there is another possibility, this one. Okay, so before entering the things, first I want to make some introduction. How can I find these things? Actually, I am an amateur just for curiosity. I'm researching another anomaly, but after that, with rotating magnet, I am using that things. After that, I noticed that a rotating magnet repel another magnet nearby. Oh, I didn't say such a thing in the textbooks. It really didn't understand, but it works. Anyway, maybe say after that, it is about 10 years ago. After that, I experimentally discovered the effect, but I didn't know the reason. Anyway, some professor suggests some things that partially solved, but it doesn't solve exactly until 2070. We are talking on the WhatsApp with a friend. Is a mechanical engineer, sophisticated on acoustics, and he's a acoustic engineer, knows everything. He mentioned that phase relation in this oscillations on every oscillation system. There's if you are driving a system, speakers. He's also engineer work on both. He thinks that there's a very critical phase relation with the speaker, the sound, volume of sound, and the speaker movement. He explained these things. The phase relation, I didn't know. Actually, in mechanical engineering, you should see that, but the textbook doesn't mention too much these things. It can be completely, doesn't keep in our mind. So also in university, I study mechanics, but I forget it. Okay, so we talk this one at the night. I sleep, and the morning I realize that should be a opposite phase working to produce this effect. I am very, very happy, but not possible to prove it, because there is a need of spectrum unit to monitor the phase of the motor. You see, if you see this setup configuration, and you see to monitor the phase of the oscillations. No high-speed camera, nothing. Difficult, but I'm convinced that this is okay. Later, I will return on this issue, the phase things. Now back to magnetic bound state. Maybe just I read some seconds how to follow this. Sure. Sorry. Searching talks. Topics. Let's see. Okay. Okay. First, what is magnetic bound state? So more officially, magnetic bound state, I call it. You can confine magnetic motor. It can be dipole magnet, simple, or multipole, quadrupole. But dipole or quadrupole, enough. We don't need more poles. With a originally rotating field. If you have a rotating field and you have a magnet, you apply a torque, and the torque is rotates also. Very. I generalize this as a cyclic torque. Even it might rotate but simply oscillate, but just right now just limit with this rotation. So when you subject a magnet on a rotating field, you drive it and it oscillates. Okay. Actually, you can do these things with other kind of force, electrical force. You need to apply a free body cyclic force, cyclic torque. Actually, important is the torque. Torque maybe use moment. Most of them they are using moment, but also we are using magnetic moment. So I'm using the term torque. So when you apply a cyclic torque, you drive a system. Originally, you have a motor mount a magnet on it, but the magnet, the pole is not like that, but oriented radially. So I can show, for example, an example here. Here, this is the magnet attached to the motor, and this is the I'm calling a different floater. I name it. The orientation is like that, and the pole of this floating magnet, something like this. Maybe I didn't too much take it, but N pole is little up and S pole is little down. And what has happened? The average field has a static S pole here and N pole here, and it statically is pulled the N pole of this magnet like that. He wants to orient this magnet on this position, on this axis. But as this magnet rotates, it's deviate. It wants to parallel to this field. Actually, when you, this is the magnet, but the field has on the opposite direction. You want to orient on this orientation. But as this thing rotates, never find this correct orientation, never become parallel. Even more, there is a very interesting effect that actually it becomes anti-parallel. It is very difficult to foresee these things before, but when I told you this engineer, the acoustic engineer told me, actually we know that this in oscillation this opposite phase relation. For example, maybe when you play on the in childhood, put a mass or anything that and put a spring here, and if you make like that, if you make slowly, it's moved like that. But if you make faster this one, it's moved like that. So you are familiar on that, the opposite phase. So the same things happen here. But the consequence is very interesting. Just this, not only simple the motion, but the magnet orient in the opposite side. This is very difficult to foresee before experiencing. Okay, so when it's become opposite side, anti-parallel, it's become repulsion. It's called a repulsion. So this is the main key issue of the magnetic bound state. There is a repulsion here. Also, there is a attraction on the axial side. So in my briefing, I write such a thing. So, okay, in my abstract, there is a sentence about this one. The axial component of the field and the magnetic fields are work in attraction, but the radial component or XY component on the XY direction work on repulsion. Okay. This is the general view of how this magnetic interactions works. Maybe we can continue here about more how the confinement happened. We have an attraction, okay, and a repulsion, but there is no reason they can find a stable equilibrium. Maybe possible. The stable equilibrium happen here, and it's very robust actually, unless you ensure the opposite phase condition.
Maybe it might be help them to see the video of your repulsion.
Exactly. So I want to. This is no. Here, wait. Yeah. So this is a historical video. It's May year 15. I didn't yet discover this effect. Just experience it. That's the repulsion. First, I'm stopping and showing what's happened here. Wait. So there's something like hide. Yeah. Okay. Okay. Coming back here. Okay. This. So there's a toy motor at the right, and there's a magnet here. Is pole. They are pole up and down. Such a thing, and this you see another magnet attached from the poles, but it's not important actually. We can attach the pole in every position, and this is working. So once I experienced the repulsion I mentioned before, so I want to see it. So this pendulum is going to crash this magnet, but actually it doesn't crash. When it's come closer, it doesn't touch. It's immediately repelled. Very interesting things. But also, you can see it. This magnet always going like that, doesn't go anywhere else, but there's some actually there is also an attraction. It's attract, but it repel at the very close distance. Then I realized that that can be used for levitation. So, okay. Then I try this same day. Still, it is not levitating, but almost levitating. I hold the magnet with the thread. It is holding like that. Actually, you see, almost there is some stability issue, but it's confined actually. Okay, this is my workshop, my room, Istanbul. This is the repulsion. So maybe right now more detail we can work about the repulsion. But first, this the important is the floating magnet doesn't immediately pull up to this rotating magnet. It keeps its pace in some direction. So and it is a repulsive direction, but also not only if you have a homogeneous field, there is no torque, but both of them they are magnet here, dipole magnet. There is also forces, actually the repulsion as an anti-. But also there is a strong force in the x-y direction, not only in the z direction. And this magnet actually little orbit, this one, but because the rotation is too fast, it cannot go too much. But actually, a fraction of millimeter, it vibrates, translational vibration. This also same principle. The phase effect is also effective is here, and it's also helped the repulsion at the cause. So there is actually two effects, and one is about the antiparallel alignment due this dynamics, angular original, and the other one is translational forces. The average of the translational forces actually in x-y direction nullify them, but in average they nullify, but dynamically, because the phase effect, this causes a repulsion. This is the so how this is obvious because I can experimental as actually this experimental result. There is no mathematical analyze here, but how this things works, how the mathematical model can be show that. In several years I work on that, but I'm trying to derivate first and take the second derivative of spherical coordinates, and a lot of them there's a lot of Coriolis term. I'm trying to eliminate them, but at the end I couldn't succeed the spherical coordinate, you cannot obtain the Newton law location, F equal ma principle. Then it is not possible. But actually, I know how this thing's moving. It's move like that. Right now, I will show this video. This is important. Wait. Where is it? Yeah, okay, here. No, this is X here. This is a slow motion video. Here is the, okay. There's a spherical magnet here, and one pole is like that. I put this one also, this enhance the effect adjustment, and this is the other magnet. So when you see in slow motion, actually this pole attracts this pole. Yeah, so sorry, so I'm pointing. This pole attracts this pole, but this magnet, instead of looking this one, look to the other side. This is the phase lag of 180 degrees, and actually this is not slow motion, but a stroboscopic effect. I put a very intense light on the things, very close, and the camera shutter speed become less than 1/1000th of second, and if you arrange the motor speed to frame rate of the camera, you can take this stroboscopic view. This way, I can see this phase lag actually happened.
What we see here is not the exact speed, but just...
Yeah, this is not exactly the stroboscopic.
Yeah, its frame are just matching with...
Yeah, frames are matching exactly.
So that's
And
why we see that.
yeah, even it can turn on the other side. If the, for example, it stop and smoke, but actually just this is the showing the phase. Now in the same, okay, this enough. So I will go this one again. Where is my? Okay, this is the same of this, but you can see the pole more clearly. Another. Thanks. Okay. Then I draw the diagram of position of magnets here. Little exaggerated this NS, but it is like that. This is very critical angle. Normally, it should be you start to this cause the attraction force. This is the reason of the attraction force. You see, and there is a virtual NS magnet here because of this distance average field cause a dipole here, and this magnet try to align to this one, NS. But actually, because of this oscillation, he never go straight here. Okay, this is the scheme of this things. Anything here? These are different things. This is a quadrupole setup, so we are later we can see it. This is the things. Actually, it's very simple. But in the first try, it is difficult to immediately get a success. Because first I say this angle is critical. It is too steep. There is too much attraction, and these magnets go closer here. And because of the nonlinear effect, is destabilized very quickly. And when it's destabilized, this magnets make tips like that and jump away. One more thing, maybe we can show you better here.
We have the PDF down there.
Yeah, okay, deny.
No, you can open the PDF. We have it saved.
Okay. So this you incline this magnet like that, but the field is not exactly parallel to this field. Actually, there's a relation. The angle of this field and angle of the magnet dipole and the angle of the field is related with a tangent relation. I can write it here, maybe.
Yeah, next to it.
Press this one. Okay. Tangent, say this is tangent gamma equal 2 tangent f oldu tangent zeta. Say zeta is the angle of the dipole, and gamma is the angle of the field. There's such a thing. You can derive this formula directly. But this is a very interesting formula. So returning these things, the angle. If you move this, change this orientation of this dipole magnet little, actually in small angle approximation, it is gamma equal to zeta in this case. So again, maybe going here, no, here. So, for example, if you make this angle 4 degrees, and the field is about 8 degrees. Normally, if you experience this and start this, and you should start with 4 degrees. 4 degrees is enough to hold this magnet, but not close. If you carry another weight of this magnet, you can go more than 8 degrees. More than 8 degrees to 10 degrees. And what is 10 degrees here? Make it 20 degrees here. Actually, you apply about 1/5 of the force to this magnet, and but repulsion is not so strong, this attraction, because you can see it, the radial component is a sinus of this. Maybe okay. Okay. Let's see. Get the pen. Where's the pen? Okay, how to say? Wait. How to show it this one? Okay, this is the x-axis. This is the magnetic moment. This is the theta angle, and this is the field here, magnetic field, like that. Because this angle is small, the repulsion is only the sinus of this angle, sinus theta. So, because this angle is small, actually, this is the amplitude of the vibration. It's about sometimes only few degrees, even less, but it's enough to make a repulsion if the attraction force is weak. So, because of this angle is generally small. The attraction force, the tilt of this magnet should be also small. This angle should be small. Otherwise, it's difficult. This is typically 4 to 8 degrees. If you pass 8 degrees, it's become unstable, very difficult to maintain. And so this about when you start to experience this one, this is important. You should start with less tilt. I'm calling this angle. Actually, should I write? This is the x-y axis, and this is the B field, and this is the gamma angle. This gamma angle, sorry, I write here, it's wrong thing. This theta angle. This is I'm talking about gamma angle is 4 degrees to 8 degrees. Okay, the theta angle change, this is very important about the stability of things. And normally in stable configuration is only few degrees. Now, how the equilibrium, stable equilibrium, how this stable equilibrium occurs? I mentioned this magnet oscillate like that, oscillate like that, and the amplitude oscillation is theta, okay, and when the field strength increase, the oscillation amplitude increase, and when the amplitude is increase, it causes more repulsion. Meantime, this is the only torque effect. The amplitude increases with the torque. Also, the force also increases with the distance, still with the strength of the field, and they are sum up. In torque, the distance of distance on in a dipole-dipole interaction. In dipole-dipole interaction, no, it's in field-to-dipole interaction. Sorry. There's in dipole-dipole interaction, the magnetic torque ratio about 3 power of the distance of from the center of the magnetic moments. But the force about fourth power, or inverse is changed with the inverse force power, and the torque increase change with inverse third power. So this angle move approximately 1 over R3. Also, the force come with R value 4. Its sum is 1 polar R7. So this is the approximately this is the how the repulsion change with the distance. If you draw a diagram here, as the one curve is like that, and other one, this is, for example, this is the attraction 1 by R4, and the other one even like that. This is the repulsion force. It's more sharper here, but if you arrange these curves, the strength of this force curves, let's think again. Ones go like that, and this is go like that. There's this is the equilibrium point. This curve, one has different power, and they are cross. And this is also equilibrium point, but also stable equilibrium point. So if you in detail, if you go this way, it's called repulsion at this point. This is repulsion, and this is attraction. So if you go this way, it causes the difference is the cause repulsion, and push this way, and attraction pull it back. So this is a how this stable equilibrium. So I have a cleaner diagram here. So you say that you open this one, not browser. Okay, wait. Here, okay. Sorry. So I can show you the more clear diagram here, but the essence is like that. So maybe we have half of the time already passed. We can.
Already almost finishing.
Okay, so we can right now show some configuration you can try. So I can go right now to web page. Here. Okay, this is some my highlighted experiment. Let's see what is that. This 4 millimeter micromotor is spinning at 100,000 RPM, and this is very small. This is an injector tip. Sorry. Okay. So these things work in very small dimensions, in milligrams actually. Then go back. So this is very, sorry, how this is skip. Okay, so what I'm doing here, it's working. Okay, so the similar the other video there. This magnet is here, and attach an steel part and put another magnet here, the same magnet, and what will happen after that? So this magnet speed up because there's a little eddy current here, and it causes this magnet also rotate, start rotating. This you will immediately, when you make experience, you will see this annoying effect. And something interesting happened here. Maybe I can open the sound right now. Okay, so in this case, it's become almost in the rotating in the same speed. When it is, if there's a, both of them, this one is a spherical magnet, and if they are rotating in the same speed, repulsion effect disappear. Only transaction things still working, but because the equations no longer work. Then maybe right now what I'm doing here, I pass it, I put another magnet down, and we have a challenging setup. It is chained, but it's not can be too much. Okay, then what can I show you? Highlight here, not too much. You can carry really heavy weight, about 300 grams for 300. I passed through more than 300 with small magnet. It can carry this heavy perfume bottle. So not too much interesting, but it's carry these things. Okay. Then videos, popular video. I will show you this one, and this not this is a different scheme, but I will first what I am doing here. I'm not putting right now. I'm trying to make a horizontal confinement trapping. Gravity pull like that. I'm now adding at some eddy dumping to prevent, but it is not completely prevent these unwanted oscillations. So it is work like that, but you need stronger interaction here. So I will show you these things first. What is that? Actually, instead of tilting the magnet, I shift the magnet. The center actually of this rotation is here. Is completely, and this is the balancing things. So it's also work similarly, but the field is complex, and this method is effective. But it is difficult to balance the motor manually. I don't have any balancing mechanism. So this is working like that. Okay, more. This is sorry, skip. This is also stroboscopic, and you can see the final effect of this, like my accordion, like that. This is a anti-Helmholtz configuration, and poles looks to each other, and the field like that, radial field, and it's holds like this. The effect, this distance is less, but there is some interesting things here. Though this magnet not only rotate like that, but only rotate in linear position, in one axis, not in a rotating axis. This can be useful for attaching to making assembly with simple pivot.
That's not. It's a rigid body, right? It's not.
Yeah, it is a rigid body, but from the camera, this name is a rolling shutter effect. Okay, this is done, and there's a. I want to show you first, but this is here, I think. No, it is here, but it doesn't show first. Short. Wait. I want to show also this one. How to. So this is there is a tree magnet here in the documentation I have, and this complex interaction. There's a lot of opposing forces there, and keep the magnet radially. So it's look actually I made an orbital motion with magnets. This may be useful, maybe not. I don't know for the applications. And I have this is important. So I will show you another first things. Instead of making a rotating magnet. Here, the static magnet, I put the opposite things. I hanging the rotating assembly under the roll starting field, and I make a what do you say, maglev model. So as you apply rotating torques, it doesn't matter how to make it. You have a lot of possibility here. The only here the gradient, there's no gradient. You need a magnetic field gradient for the effect, but on the this x direction, say there's no gradient until the end. Only the gradient in the transfer direction, and still working. A part of the forces work there, repulsion force, but still you can use them. Again, going back here. So, for example, you can duplicate this one, two motor, and you can make a train car. Actually, you don't need actually the in vertical direction, horizontal things also work. If you put two rails like that, and to put two rotating magnet in the between, you can move this like a train wheel. But there's a challenge: the stability. Two interacting oscillations generally interact each other and doesn't work well. So there is a need some solution, spatial engineering requirement for making this more reliable. Actually, I make one thing, but it's very marginal stability. And more than, yeah, this is also interesting. Maybe you are interested. Sorry. Okay. Now I make 3 drums. 2 of them are working in the same clockwise, and other one in anti-clockwise. Otherwise, it's not 3. If you are 3 motor, you cannot make the opposite maybe. So you can hold this magnet in the middle like that, and the distance is little increase. There is this rotating field is interesting, and actually as you can vibrate the center magnet, every solution works. There's a lot of, I make two magnet, 2 drums distances, everything actually works, but you need to little try adjust the RPM speeds and other things. Then finally this distance, and they can finally work. They make a lot. At that time, actually, I didn't know the exact principle of all this magnet. Later, I write the equations. Just finally, I'm going to the equations there. Where is it? Oh, it's not here. Sorry. Here. No. Here. The other one is still is not working, but this is working. Okay. I write this is a Python application program just for developing equations, simulation, and make the analysis. This will be free after I publish it. These things only I cannot give you right now how to use it. There's a guide here and sections here. So I can maybe like that better. This is stupid. Okay. How I can derive the equations of motion here. I explain first I make a earlier rotation matrix. I use XZ, ZXZ scheme. Maybe most of people use XYZ scheme, but I'm using. I see this one also COMSOL program use this scheme, and it's exactly fit these things. So after dissipation term, if you have a damping, you write this things, and I write this is the magnetic field vector. I define like that. This is you see the gamma angle here, the tilt angle. Actually it is not a zenith angle. Zenith angle, the opposite. How to say? Otherwise, it's make cotangent, but the angle I don't know what is the angle. So this is the magnetic moment in spherical, just a spherical coordinates. Only name this. This is the phase of the azimuthal angle, and this is the zenith angle. This is the moment of inertia, and after that I write from here this is the kinetic energy. Just writing, you can derive this like that, but in order to derive it, you need to. Okay, this is. So for calculating kinetic energy, either you need the moment of inertia vector in local coordinate, or you can use in global coordinate, and this is the velocity vector of the body in local coordinate or lab coordinates. That's all. This is the magnetic potential field, very easily defined. And then I write the Euler Lagrange equation. Actually, the Newton equations also works the same, going to the same result. But once it's delayed to me, because I always think that Lagrange Euler Lagrange equations work on conservative systems. But this is not a conservative system. It is a driven system, and you input energy. But it works. So how it's work? Because the force and torque come from potential, come from the difference of potential. If you have force and torque can be derived from the potential, even they are time dependent, this potential, Euler Lagrange equations work. I don't know, I didn't see too much in this textbook, but I think this is correct. So these things, okay. Then this is the full rotation matrix, standard rotation matrix in x, y, z, z coordinates, and this is same things. This is angular velocity vector in body coordinate and lab coordinates. Then this is a full equation of motion with three diagonal. Moment of inertia is very long, but if you have axis symmetric body, it's significantly simplify like that. Even simplify if you have a isotropic body, like a spherical sphere, it's simplify. And now you can see the term how it's work. You can analyze with your logic without just seeing that, you can see that these things. So what is interesting here, when you see this equation of motion, normally in an oscillator there's a driving term and there's a stiffness term, and this is dissipation. This is not important right now, but actually there's a stiffness term here, but it is not how to say main term. The main term, the bigger term in the experiment, in realization, is this term. This is the speed of the rotation field, and the one you see it in the first. I forget these things. How can I say? In order to make this rotation look like that, you need to implement two rotation matrix. If you go back here, go back here. If we have phi and psi and phi, how to spell in English? Psi, I don't know. This is phi actually, phi and psi. So they should be in opposite sign. When they are in equal opposite sign, this thing, there's a still it moves like that, but it doesn't turn. It's always looking this one to you. So I'm accepting this is a default formulation because equations is easy to solve. Then go back this equation. This term here. It is a big term, and this governs the equation actually. But when you make the numerical term here, you can see this. You can see immediately it's unstable. The stiffness comes from here, from the gamma, and this doesn't make everything should be. I'm not know. Should be negative. Should be or positive. I don't know. It is depending. But when you analyze it, it's unstable. So no way you can simple evaluation. This gives no terms. There also you can examine these equations. They give a lot of insight here. One thing here, the phi angle actually is also this term plus the log phase 180 degrees. When you put this line, put this one here, this term eliminate only less 180 degrees and make a negative sign here. And this term is also placed. So in equilibrium position, the t variable disappear. It's very interesting. Actually, you can see all the experiment, everything. When the t term disappear, it's become static solution in rotating frame of coordinates. So even this angle phi, these things, you can make a mechanical actuator like that. You can do this mechanical model of this motion when you change these things. Okay, so Then I have this, what is that?
We were getting
Okay, so I have also a simulation here. I can show you these things. This program also make not only this one. You can, for example, make it, intermediate access theorem, tennis racket theorem. You know, this. You know the name of this astronaut, difficult to spell. You know, it's make a space station. It thinks a screw rotate like that. After that, it's switch these things. You can also simulate this effect here. We have lot of things here, but right now we have eigenvalue analysis here. Actually, immediately make an. There's also empirical formula. I have one empirical formula here. Even I cannot find the origin, but it's working exactly without exception. It's very challenging. I have the right now. No, I need to change this one, for example. Another one. This everything's okay. Let's see. This is. I should say this one also, but right now make it. You can give some damping. But sometimes, yeah, it's not automatic here. Everything is okay. This is the minimum gamma angle to obtain the stability. It's automatically calculated. Actually, this is the empirical formula. Right now, just make this. I can make this thing first. Make eigenvalue plotting. Here, this is the gamma angle. How the stability eigen vectors change with gamma. This is real part. One real part positive, one real part negative. This unstable because this part is positive, but I give little. You can see it's meet in zero, but actually, if I can zoom here, this part also go below zero. Now it is stable. And here, go back here. And this is the imaginary part. So, in unstable regime, there is a one frequency, but in a stable regime, there is a bifurcation. They say bifurcation. Two frequency diverge here, and you can see this imaginary parts show some frequency. And if I can make a simulation, let's see the simulation what show. Actually, I can show the animation of this at the same time. Yeah. This is not so stable, I give it. Let's zoom it back. Okay, for example, I didn't give a good. Yeah, you see this blue things. I give the gamma angle. Actually, the stable angle start here, and from the plot, you can see that first it makes little go for 2 seconds. Okay, after that it makes such a oscillation. The oscillation actually is unstable, but because of the nonlinearity, it doesn't blow. For example, I can, no, because I give 0. But I can increase the gamma right now. Okay. Let's do again, everything is okay. What we can see it. Because damping the oscillation, this is natural frequency. Because I didn't give any bias for, but this gets some initial condition. Even start from this, I don't know why this oscillation grow and they make it beating. There is a frequency measurement here. They found 2 frequency here, and let's check it from here. If you can see it, show you. Is there close? This is radian. Sorry, this is radian. You need, yeah, also radian here. No, radian. What do you show? Yeah, this is real part. Sorry. Here, 180 degrees, and other one. No, this is the this is unstable. We need to replot this one, I think. Yeah, right now this is stable one, and imaginary part. Yeah, 182 degrees, and other one 187 degrees. The eigenvalue find, and you see it's holding, and even it's holding for significant digit, sometimes 5 significant digits. So this is a good way that you write the validation of your equations is working and your analysis is working. Also, I make this simulation compare with the COMSOL program result is holding, but this one is about 1 million times faster than COMSOL, and it's very accurate because it's using the equation of motion. COMSOL just apply the forces, torque is calculated, and the system make it. This can be this faster. Otherwise, I work for COMSOL for developing these things, and very painful. It takes several days to finish a simulation. Okay.